Today I'm going to be talking about recursion. My name's Hunter. I'm a software engineer, 4 years of experience, and 6 to 8 weeks ago, I couldn't define time complexity. Since that time, I've been working on my computer science fundamentals, and next up is recursion. So without further ado, we're going to get into it. The stuff that I'm going to cover today is actually from chapter 10 of A Common Sense Guide to Data Structures and Algorithms. It's been a great textbook for me to get the fundamentals that I need. And so this is just an opportunity for me to kind of go through that material and teach it myself. So the first thing that we're going to do is talk about recursion. If you've heard of recursion before, it can sound like a confusing topic, but all recursion really is, it's a function calling itself. Okay, so what is recursion? And give me an example of recursion. Let's talk about it. So if we had this Python function, Hunter, we could call our function within the function. This function doesn't do anything, but it's recursive in that it calls itself. So let's take a look at an example of this. So we have a NASA countdown timer. Okay, so the idea of this is you have a timer that counts down from 10 to 0. So it would do something like this: 10, 9, 8, 7, etc., etc. Okay? So if you were to implement something like this in Python, you'd probably do something like this. Def time represents some sort of integer value, and you would say for I in range time 1, -1. Sorry, time 0, -1, print I, and then to call this function, we would do something like this. And this would give us the desired result of 10, 9, 8, 7, 6. So this would be probably the route or avenue that most people would take. But what if we did this recursively? So we could, again, do def countdown. And this time, we're going to print time. And we're going to call countdown time -1. What this is going to do is actually go, and so this recursive function operates a little bit differently. So now if we were to pass a value of countdown 10, what this is going to do is print 10. If we do countdown of 9, again, we're going to print 9. Countdown 8 is going to print 8. And so I guess what I'm showing is that you start with 10, and then as we go through here, the next call is going to be 9 because we decrease our time value by 1, and then we do the same thing here. Now, what's tricky about this, with the way that we have this set up, is that at some point we're going to get to countdown 1. This is going to print 1. We're going to print countdown 0. Again, that's going to print 0. And then we're going to do countdown of -1 equals -1. Now, in our original discussion here, all we wanted was a countdown timer from 10 to 0. And because we wrote this recursively, we don't have a way to stop this timer from continuing to run. When you write recursively, you have to implement a base case. A base case is simply the case that exits the function or stops the recursive case from continuing. So if we were to rewrite this function, we would say if time equals 1, print 1. Otherwise, we print our number, time, and then countdown time -1. And so now this is our base case. Our recursive case is here. And so now, once we get to a time of 1, we're simply going to exit here, print 1, and we'll be done. We'll be out of this recursive case. And so that's the importance of base cases, is that it basically stops your recursion from continuing. So now, if we were to include a base case in our countdown, here's what we'd want to do. We'd want to check, is time equal to 0? If so, return. And in this case, we're not going to return anything. It's just going to exit our loop. Otherwise, we're going to print time. And our recursive case is time -1. This is our base case and our recursive. And so the whole point of a base case is just to make sure that your function doesn't run indefinitely. Otherwise, it will just keep going down the stack, especially with a countdown timer like this. And the next thing that we're going to talk about is how to read recursive code. I think at first glance it looks a little bit confusing to read, but we'll walk through an example and hopefully it's a little bit more easy. So a factorial in math, something like this. 4 factorial equals 4 times 3 times 2 times 1. This, of course, equals 24. So if we were to calculate a factorial in Python, we could do something like this. We'll have n be our number. We'll say if n equals 1, we'll return 1. Else, return number times factorial n minus 1. So if we look at this code, I think at first glance, it's a little bit confusing to read. But the way we ground ourselves here is we identify the base case. And so because of the last problem, we know that our base case is if n equals 1, we'll return 1. Okay, so now we know what this piece is. The next piece is going to be walking through this function for the base case. And I'm gonna move this stuff over. Okay, so we've identified the base case. Now let's look at our function when the factorial of, if we have a factorial of 1, okay? Factorial of 1 equals 1. All right, now we go to the second to last. So we look at the second to last case. We say, okay, factorial of 2, what does that equal? Well, that equals 2 times factorial of 1. Well, we know that equals 1. So we say that factorial 2 equals 2. Now, if we continue on, we'll look at factorial of 3 equals 3 times factorial of 2 equals 6. And so you can kind of go through this process and make a small note here, walk through next to last. And so what I want to show here is that each of these build on top of each other. In order for us to know factorial 2, we had to know factorial 1. In order for us to know factorial 3, we had to know factorial 2. And again, like if we start at the base case, this becomes so much easier because we just get the function to a state which we know the return value. So in this case, we have factorial of 1, n equals 1, we return 1, okay, and then we just build on it because now we're able to get to this recursive case. So if you go through here, you identify the base case, you walk through the base case, then you identify the next to last and kind of repeat. This process should be much easier. So what's important to note here is that going back to our previous example, if we have a factorial of 3, we actually aren't able to finish this run until factorial of 2 runs. But factorial of 2 has a dependency on factorial of 1, which is our base case. And so for a computer to keep track of each factorial call, each call must be appended to the call stack. For those that are unfamiliar, a stack is a last in, first out data structure. Recursive functions require a call stack to keep track of each one of these calls. So again, if we have a factorial, let me give myself some room here. If we have a factorial of 3, this would be appended to the stack. As we mentioned, factorial of 2, factorial of 3 has a dependence on factorial of 2. Factorial of 2 has a dependence on factorial of 1. However, because 1 is our base case, as we defined before, if we have a factorial of 1, that returns 1. That's our base case. We don't push factorial of 1 onto our stack. So if we start with factorial 3, it'll be the first item pushed to the stack. The next up is going to be factorial of 2. And then factorial of 1 does not get pushed to this call stack. So as we get to our base case, in this case factorial of 1, the computer says, okay, I have factorial of 1. Now I'm going to do factorial of 2. And so what happens is this factorial 2 is popped off of the stack. It is removed from the stack. And then once we have the answer to factorial of 2, we go to factorial of 3. And finally, factorial of 3 is popped off the rest of the stack. And so that's how a computer keeps track of each factorial call because they have dependencies on each other. Another important concept is stack overflow. And so this occurs when a function repeats indefinitely. And we know that recursive functions will repeat indefinitely if they don't have a base case. And so if we go back to our countdown timer and we didn't have a base case, we would continue to go down the stack until the computer no longer has enough memory to allocate towards all of these function calls. And so what happens is you have a stack overflow where there's no more memory that can be allocated to the computer. And so you'll get an error like stack overflow, which is why it's so important to have base cases for your code. So at this point, you might not be seeing a ton of value in using recursion versus using a simple for loop to do what you need to do. I think a good example of where recursion really makes sense is exploring files in a file system. Let's say that you have you want to print, given a directory, print all the files that are in it. So given a directory, print all files in directory. Now, I'm not going to write a full function that would do this. So we're just going to write some pseudocode. So like, let's say we had def file system with an input directory param. What we would do is check, you'd simply do something like, are there files in here? If so, print file names. And so if we had a directory like documents, and we had files like, if we had a document structure where in our documents directory, let's say we pass this documents directory to our file system, our function would be able to print these files well. But if we have an existing subfolder inside here, we don't know the contents of this directory unless we hard-coded it. And even if we added a layer deep, this could have a cooler folder underneath. And so what's important about recursion is it's best used when you don't know how deep or how far you need to go. So that's really where recursion shines. Now, with this similar example, we'd have our logic to check for files, and I probably shouldn't have erased that. Check for files, print. Now, we'd have a base case defined, but then if we had any subdirectories, we would just call this file system method inside of here. And so how this would work is if we're given documents, we have all these files in here, we're going to print all of those. But if it detects a directory, it's going to go in here and look at the values in here. Similarly, we can keep going all the way down until there's no more subdirectories. We're going to print all of the contents. So file system exploration is a really good example of how this could work and what you could do here. All right, and so that's a basic introduction to recursion. I hope you enjoyed. Next video is going to be exploring recursion a little bit more deeply, and we're going to write a little bit more functions. So thank you for watching. Let me know if you have any feedback. Let's keep building. All right, so that's a basic introduction to recursion. And in my next video, I'm going to look at writing more with recursive functions and doing a little bit more hands-on work. So if you enjoyed this video, that one's coming soon. Thank you for watching. Let's keep building.